Welcome to AP Calculus Chapter 6 review. I'm going to do this review in 3 sections due to some time constraints. Let's get started. Make sketches illustrating RAM for LRAM 4, RRAM 4, and MRAM 4, and this 4 indicates we're going 4 partitions, which is very convenient because we're going from 0 to 4. Had we been going 0 to 2 with 4 partitions, I would have set up my T-chart to be 0, 1/2, 1, 1.5, 2, but nice convenient partitions on the integer. So let's go ahead and complete this T-chart, and then we'll get some graphs set up for it. Put in 0, get out 2, put in 1, get out 3, put in 2, get out 6, put in 3, get out 11, and put in 4, get out 18. Make sketches, and when you do this on the test, I want 3 separate sketches. We're going to have a little LRAM section, an RRAM section, and an MRAM section. So let's go ahead and set up our LRAM graph. I notice my x's just go to the right and my y's are all above the x-axis. So I need some room up to 18. 1, 2, big graphs, don't get sheeted here. And I need room for 18. So let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. So at 0, I'm at 2. At 1, I'm just up at 3. At 2, I jump up to 6. At 3, we're up 11. At 4, we're up to 18. Take your time, make a nice big graph, make it look good. So my function looks like that, and now I need to partition that into 4 spaces. So again, it's on the integer, wouldn't have to be on the integer, so we're trying to find the areas of that utilizing LRAM. So my LRAM rectangles, my first partition, LRAM, I go to the left, I track up to the curve, and I just build my rectangle across. My second partition, I go up the left side of it and build my rectangle across. My third rectangle, I go up the left side, and my fourth rectangle, I go up the left side. So this is what I would use for approximations. Okay, we'll get back to that. I'm just going to go ahead and complete my graphs for RRAM and MRAM. So RRAM, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And let's get going on that one. Put in 0, get out 2. Put in 1, get out 3. Put in 2, get out 6. Put in 3, get out 11. And put in 4, get out 18. And now for my, so we're looking at our partitions, excuse me, along here. That is a bad one. And now for my RRAM, on my first partition, I go up the right side, and I build in my rectangle. Second partition, go up the right side till you hit the curve, build in the rectangle. So on our third approximation, we would be finding the sum of those 4 areas. And MRAM. Same curve, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 0, 1, or excuse me, 0, 2, 1, 3, 2, 6, 3, 11, and 4, 18. And MRAM, we should show that we're coming up the midpoint here. So right up here gives me a point. Coming up to the midpoint, I get this curve a little over on the left, a little under on the right. Straight up to the midpoint, building our second rectangle. Straight up to the midpoint. And this is a pretty good illustration that shows why MRAM generally may be a better choice, because we get that overestimate maybe compensating for that underestimate. Doesn't mean it's exact, but it might be a better choice. We would expect most times, depends on the overall shape of the curve, but most times we expect that to be better. Okay, so let's go ahead and actually find these guys now. So write out by hand LRAM. So here's my LRAM. I'm just going to call it L equals, this would be 1 times the height of this. Well, the height of this is 2, plus 1 times the height of this. The height of this one is 3, plus 1 times the height of the third rectangle. The height of that is 6, plus 1 times the height of the fourth rectangle. The height of the fourth rectangle is 11. So we get 2 plus 3, 5, plus 6, 11, plus 11, 22. And we wouldn't even put approximately equal to. The area under the curve is approximately equal to, but our LRAM value is 22. Okay, RRAM. R equals, first is 1. I'm just going to factor that 1 out. We notice we could factor that 1 out of each of these. So 1 times the height of the first rectangle, well, going up the right side, we have a value of 3. Going up the right side of this is f of 2, that's 6. Going up the right side of this, that's f of 3, 11. And our last rectangle, f of 4, 18. And we get 9, 20, 38. And MRAM, we got a little bit of work to do here. I need to put in 1/2 into this function. And at 1/2, I get 1/4 plus 8/4. 1/4 plus 8/4, I get 9/4 here. At 3/2, I put in 3/2, and I square that, and I get 9/4 plus 8/4, 17/4. At 5/4, or 5/2, excuse me, I get 25/4 plus 8/4, 27/4. And at 7/2, I get 49/4 and 8/4. 49 and 8, I get 57/4 for my height. So my MRAM approximation, again, would be 1 times 9/4 plus 17/4 plus 27/4 plus 57/4. I'm going to be lazy here. Second quit. And I get 9 and 17 and 27 and 57. I get 110/4, or 55/2. Okay, so write out by hand, LRAM arm dead. Do not use decimals for any portion of this problem. Didn't. Should be good to move on. Okay. Number 2, I think just for the interest of seeing what's going on with this, I'm going to change this to 4. It might be 4, it might be 10 on your test, but I just kind of want to show what's going on our estimations here. Estimate the area of the region between the graph F and the x-axis, x equals A to x equals B, by using RAM program for n equals 10 and 100. We're going to use 4. Do all 3 RAMs, LRAM, MRAM, RRAM, compare and find results. Write out all decimals, no rounding. Make sure you're in the correct mode. Okay, so let's get zoomed in on this a little bit here, so we can see our function. And I'm going to go into my y equals, clear this, 1 plus sine of x on x, make sure I'm in radians, which I am. 1 plus sine of x on x. And go ahead and quit that one. And now I'm going to go to my program, and I'm going to run my RAM program. And intervals 4. And left bound, I'm not going to approximate this, pi divided by 2. And right bound, 3 pi divided by 2. Enter. And we get those pretty quickly because it's only 10. It's only 10 approximations. So let me get those copied in here. My LRAM value, 3.091896751. My MRAM, which is my third, 2.7500. 43664. My RRAM, 2.4504. 75394. And I'm just going to rerun it again with 100 intervals. And this may take a little bit longer for the program to run. So again, second pi divided by 2, and 3 second pi divided by 2, and it's thinking. And I've got an additional Simpsons rule on here. So let's take a look here. So we have 3.367865781. MRAM, careful, 3.3544569932. And RRAM, 3.34115768. Okay, so we've got that portion done. And let's make sure. Do all 3 RAMs, did it? Compare results with FNInt. Okay, FNInt. So I'm going to go to Math 9, back in here, and I want to be integrating again from negative pi on 2, or from pi on 2, excuse me, second pi divided by 2 through 3/2 pi. So 3 pi divided by 2, and I could type the function in here, but I could also go to vars, y vars, variable 1 dx. And I get 3.379. Let me go ahead and copy that into here. 3.379203239. And we'll lock in our zoom here for a second on my awesome hover cam. Which approximation is most accurate? Well, which one's closest? Here I have 3.367. That's about 0.012 away. This is further away. This is further away. Wow, LRAM. And we talked earlier, we would expect probably most times for MRAM to be our best, but apparently LRAM in this case is a better choice. Okay, number 3. These should be our favorite on here. A lot of notation going on here, but we've learned to read between the lines. This basically means we're going to find our integral from 1 to 5. And we're just going to have 4x to the 4th minus 7x squared, and this is our dx, and this is the most likely way to miss a point on this. It is not 4x to the 4th minus 7x squared times dx. It's all of this. That's the function. That's the y times the x. All right, likewise for b, this is our integral from 1 to 5 of 2 on x to the 4th times dx. And that's it. We'd love to have a bunch of these on the test. Number 4, use a definite integral. Okay, here we're going to actually integrate. To express the area, we got to be careful here. Area. Area is going to be the integral, provided the integral does not, on the interval, dip below 0. So we have to check that first. Now, the integral of this does not dip below 0. We just dealt with this function. This function, of course, is up 2 and wants to be a right side up parabola. It looks just like x squared except up 2. So we don't have any fear of having to partition this as we might on a later problem. So here we go. Integral 0 to 4 x squared plus 2 dx, all of it. Evaluate the definite integral by hand using fundamental theorem part 2. That's what we do. Do not use absolute values. Show that's a dead giveaway. You might want to expect something to cross 0 here, but not in this case. So if I take the antiderivative of x squared, to get to x squared I would have had to start with x cubed, but that gives me 3x squared. I don't want the 3. So first term, x cubed on 3. To get to 2x, I had to start with 2x, and I'm integrating that from 0 to 4. So I put in 4. Then I subtract from that, put in 0, and I get 64 thirds plus 8, or plus 24 thirds, minus big 0 here, I get 88 thirds. All right, let's make sure we've got everything. Evaluate the definite integral by hand using fundamental theorem of calculus. Do not use absolute values. Show all work. Check your solution using. I will leave that to the user to go ahead and use fn_int. I'm sorry, I didn't show all of this. Here's all of our work, but you can go ahead and fn_int this integral and see that you end up with that, approximately with that solution. Okay, now sine of x. Let's take a look at the graph of sine. The graph of sine looks like this. Here's pi on 2, and here's 3/4 pi right here. And again, we don't cross through a 0, so all of our area is above. But maybe we're going to need to, prior to the test, talk about what happens when it does, but I think we know that. We have some subtraction. But please don't let those two problems make you assume that we aren't going to have some area below the curve to consider here. Okay, we'll take a look at an example like that in class, since neither of these had it on it. Okay, so integral sine of x from pi on 2 to 3/4 pi dx. To get to sine, I have to start with cosine, but the derivative of cosine is negative sine, so I don't want negative. Oops, don't want that either. So I'm negative cosine of x from pi on 2 to 3/4 pi. Okay, so here is pi on 2 right here. At pi on 2, we could say x is 0, r is 1, y is 1, and cosine is x on r, 0 on 1. So when I put in, I should start with 3/4. Let's get our 3/4 pi here as well. Here's 3/4 pi, where we have values of -1, 1, root 2. So put in 3/4 first, and we get the opposite of. Cosine is -1 on root 2. Minus, put in pi on 2. At pi on 2, x is 0, r is 1. That is 0. So -0, so we just end up with 1 on root 2. Okay, again, we're going to be alert to when we cross 0. For instance, had this first function, let's say this first function, f of x, was x squared minus 2, and we're integrating from 0 to 4. I'm just going to get you started. I'm not going to complete this problem, but here we would have a function that looks like this. And right here would be the point. Root 2 would be a 0, clearly. If we go over to 4, then what we have to do is we have to realize this area would be considered negative, this would be considered positive, so we'd be interested in taking the integral from 0 to root 2 of x squared minus 2 dx, but that would calculate as a negative, so we want the opposite of that, plus the integral from root 2 to 4 of x squared minus 2 dx. That would calculate as a positive, so we do want it as a positive. So that would be the difference if we cross 0. So what would we have to do? We always have to check, unless we know what the function looks like, unless we know that the function stays above or well, actually, only if we know it strictly stays above, then we just need to integrate. But in this case, we need to partition it by saying, when is x squared minus 2 equals 0? X equals plus or minus root 2. Positive root 2 is a 0 that exists between 0 and 4. So we would go through that process. You can pretty well count on one or both of the problems on the test involving that procedure. Okay, in 5A, I'm going to wrap it up here. Use a definite integral or integrals to express the area between the x-axis and the graph. So once again, we're going between the area. Yep, same thing. X-axis. Maybe we have one here. Let's take a look. So if I go ahead and find the zeros of this, because I don't know exactly what this graph looks like. So I'm going to factor this. X squared minus 3x plus 2 equals 0. Let's see. X times x minus 2 times x minus 1 equals 0. So we have zeros at x equals 0, 1, and 2, which is kind of nice. We have one at 0 and we have one at 2. We have another one at 1. This is the one that's really the troublemaker here. But for graphing purposes, this is pretty nice. I've got a 0 at 0, I've got a 0 at 1, and I've got a 0 at 2. So my graph, without putting a y-scale in here, knowing that this is a positive cubic, must look something like this. Now, everything I know about a cubic leads me to believe that these two areas are equal. But I'm going to go through the entire process of this, and we're going to talk about how we would find this. So this first area would be calculated as a positive. So I want the integral of, I'm just going to call it f of x from 0 to 1 dx. I want the positive version of that. And then this area is under the curve, so I need the opposite of that. So the opposite of the integral from 1 to 2 of f of x dx. Again, I expect these two values, the absolute value of each of these, to be the same. We're not supposed to use absolute values, so don't put plus absolute value of. We're really showing that we can do this by hand. So my integral, let's talk about area 1 over here. So to end up with an x cubed, I need to start with an x to the 4th. But if I take the derivative of x to the 4th, I get 4x to the 3rd. I want 1, so I'm going to cancel that 4. To get to x squared, I start with x cubed. The derivative of x cubed is 3x squared. That's good, so just minus. And to get to 2x, I start with x squared. The derivative of x squared is 2x. Beautiful. So we get this from 0 to 1. What do we put in first? The top value. Let's not mess that up. That would be painful for us. When I put in 1, I get 1/4 minus 1 plus 1 minus, when I put in 0, I get big 0. These cancel. I get 1/4. So again, knowing what I know about this, I believe the area of this is 1/4, the area of this is 1/4, but we're still going to show our work. So now this would be our area 1. Area 2, I want x to the 4th on 4 minus x cubed plus x squared, but now I want that from 1 to 2. Put in 2, and I get 16 on 4 minus 2 to the 3rd 8 plus 2 squared 4. How about that? I've got area 0. Now, why was that not surprising? That's just the first part of it. Okay, and then we subtract, put in 1. Now notice, I already put 1 in to the same function over here, and I ended up with this portion right here, which was our 1/4. So that area ended up integrating to be negative 1/4. But we want, due to this, we want 1/4 minus negative 1/4, or 1/2. So the area is 1/2 square unit. Okay, and then I'm going to leave the remainder of this, or I'm going to pick up on problem B on the next video. Thanks for checking in.